Hello everyone! Welcome to the M2L31 series Level 1 training course. Today, we're going to walk you through an example program using the Low Power Timer with PWM. In this demo, we'll show you how to control an LED to create a breathing light effect while the MCU stays in low power mode, using auto operation mode so the CPU doesn't have to intervene constantly. You can download the example program from the link in the video description below. Once you've downloaded it, just extract the files and open the project in the Kyle development environment following the provided path. This example uses the NuMicro M2L31 series SG development board. The main goal is to show how to create a breathing LED effect while the MCU is in power down mode. The example also uses an add-on called the M2L31 series learning board, which has an RGB LED. The LED will control corresponds to pin PB5. All the following code and settings revolve around this LED, so you can clearly see how PWM drives the LED behavior in low power mode. If you want to connect your computer to the development board to monitor the output messages, make sure to enable the virtual COM port on the right side of the board. Specifically, turn on the TXD and RXD switches. As shown in the diagram, just slide both switches to the right. This way, your computer will be able to properly receive the messages sent from the development board. Next, let's quickly go over the workflow of this example program. First, the system uses the low power timer to generate a PWM signal, which controls the brightness of the LED. Then, the timer's accumulator interrupt triggers channel 0 of the low power PDMA. Once triggered, the low power PDMA sequentially moves the data stored in low power SRAM into the timer's PWM compare register. The timer automatically adjusts the PWM duty cycle according to these compare values, creating a breathing LED effect. Finally, when the PDMA transfer is complete, an interrupt wakes up the CPU. The entire process is mostly handled by hardware, allowing the system to achieve true low-power operation. Next, let's look at the relationships between peripherals from the bus matrix perspective. In this architecture, the CPU acts as a master, capable of reading from and writing to resources within the low-power domain. Meanwhile, the low-power PDMA also functions as a master inside the low-power domain. It can directly read data from the low-power SRAM and then write that data into the low-power timer. Next, let's take a look at the program itself. Starting from the main function, you can see the overall structure of the code. In this low-power timer PWM example, the actual features we use are quite limited. The key components are the low-power timer, its PWM functionality, and the low-power PDMA. These modules work together to achieve automatic control while the system stays in low-power mode. As for the initial system setup, like the minimum current init function, system init function, and UART init function, please refer to the low-power timer sample code video for detailed explanations. First, we set the low-power timer's clock source to LIRC, and then enable the timer's module clock. This ensures that the timer can keep running even when the MCU enters power down mode. Next, we configure the timer's output pin and enable the PWM function. At this stage, we also set the PWM frequency and duty cycle. After that, we store the PWM period value. This will be used later to calculate the changing duty cycle for the breathing LED effect. Finally, we set up the timer's accumulator function, including the number of accumulations and using the period as the counter. Once everything is configured, we enable the accumulator, completing the setup process. Next, let's talk about how the low-power timer PWM registers are actually set. When calculating the register values, we mainly consider three factors: the clock source frequency, the PWM duty cycle you want, and the prescaler setting. Using these three values in the formula, you can determine the value to put into the period register. But if you're not familiar with these calculations, don't worry. When using the low power timer PWM API, the functions will automatically calculate and set the necessary register values for you. Next, we have the function used to configure the Low Power PWM. The overall setup process will be easier to understand on the next page, where we'll plug in actual numbers for these variables and walk through a concrete example. First, we enable the Low Power PWM module clock and turn on channel 0 of the Low Power PWM. Since there are quite a few parameters to configure through the API, let's go through them one by one. The set transfer mode determines whether to use scatter-gather mode. In this example, we're not using it, so we set it to false. Set transfer count defines the size of each data unit and the total number of transfers. Here, each data unit is 32 bits and we have 8 units in total, but we subtract the first one, so we set it to 7. Set transfer address specifies the source and destination addresses. You can think of it like sending mail. The source address is an array that increments for each transfer, so we select INC, while the destination address is a fixed register, so we select fix. Set burst type chooses between single or burst mode for transfers. Since the accumulator triggers one data unit at a time, we select single. Finally, we enable the Low Power PWM interrupt, so that when the transfer is complete, it will trigger an interrupt to wake up the MCU. Here, we first create an array where each element represents a value to be written into the Low Power Timer's PWM compare register. Each value corresponds to a different PWM duty cycle, which allows the LED to display varying brightness levels. Next, we start the Low Power Timer PWM, and the MCU can enter power down mode. The PWM will run automatically, and the CPU doesn't need to get involved at all. Here, let's explain the relationship between the compare value and the PWM duty, as shown in the diagram on the right. The PWM output duty cycle is determined by the ratio of the compare register value to the period register value plus 1. For example, if the compare register is set to 40% of the period plus 1, the PWM output duty cycle will be 40%, meaning the LED will light up at roughly 40% brightness. Once the system enters power down mode, the Low Power Timer PWM will use the accumulator interrupt to wake up the CPU, allowing the program to continue execution. After sending out the message, we update the Low Power PWM parameters and reconfigure the PWM accumulator for the next cycle, then go back into power down. The duration that the PWM maintains its output during power down is determined by the accumulator's IFACNT register. Now you can open the Kyle project file from the path we mentioned earlier. Next, click Build to compile the project. Once the compilation is complete, connect the development board to your PC via the debugger's USB port. Then, click Download to flash the program onto the board. After the program is successfully loaded, you'll see the LED displaying the breathing light effect. You can also open a serial communication tool at the same time and make sure the TX switch on the development board is turned on, as we mentioned earlier, so you can view the UART messages. Next, let's use the current measurement software to check the system's actual power consumption. From the measurement results, you'll see that since the CPU doesn't need to be continuously woken up in this scenario, the overall average current consumption is only about 25 microamps. Looking at the program flow, we can directly observe the system behavior during the current measurement. In the graph, the two peaks represent two CPU wake-ups, which correspond to the IFACNT values set to 40 and 10 in the code. This explains why the breathing LED blinks at different speeds. You can also try modifying the loop values in the main function to see how different settings affect the LED breathing pattern. That wraps up our introduction to the Low Power Timer PWM sample code in this training session. Thank you for watching, and if you'd like to learn more, please feel free to reach out to us.